3, problem 21 reads, a man stands on the roof of a 15-meter tall building and throws a rock with a speed of 30 meters per second at an angle of 33 degrees above the horizontal. Ignore air resistance. So we need to calculate first the maximum height above the roof that the rock reaches. So to get that, first we need to find the y component of our initial velocity. Since we have a triangle here and our initial velocity is 30 meters per second, our angle is 33 degrees. To get the y component of our initial velocity, we take 30 times the sine of 33 degrees, which gets us 16.34 meters per second. Likewise, we'll need the x component later, so I calculated that, which is 30 times the cosine of 33 degrees, which gives us 25.16. So to find the height above the building it reaches, using the equation derived in class, our height will equal our Vy squared over 2g. Since our Vy we just calculated is our 1634, and g will be 9.81 since we can assume we're on Earth. We'll plug those into the calculator. We get a height above the building of 13.61 meters. I messed up my drawing here. H should be this, but that doesn't matter so much. So B, we need the speed of the rock just before it hits the ground. So we have the x component of velocity will hit the ground will be the same. Since there's no air resistance, our x component of the velocity will stay the same. We need however, the y component. So throughout the variables we know our v naught y is 1634, but we need to find our vy. Our acceleration will be negative 9.81 meters per second squared. Our total displacement in the y direction will be negative 15 meters, since that's how high the rock was when it was initially thrown. Time for this doesn't matter, so we find a kinematics equation without time, and our vy squared will equal our v naught of our y component squared, plus 2 times the acceleration times our displacement. So our Vy will equal the square root of 16.34, which is our y component of our initial velocity squared, plus 2 times our negative 9.81, which times negative 15, kind of ran out of room right there. So our final velocity in the y direction is negative 23.69 meters per second. So to get the final, since we have a triangle, we have the x component and the y component. Using the Pythagorean theorem, the final velocity is the square root of each of these squared added together. I forgot to write it down, so let me quickly recalculate it. So we have the square root of 25.16 squared plus negative 23.69 squared. So that'll give us a final velocity of negative, since, well, negative and positive doesn't really matter for this, of 8.47 meters per second. So now for C, we need to find the horizontal range from the base of the building to the point where the rock strikes. So this is also pretty simple. So we need to find, we can use our distance equals velocity times time, or our range equals our velocity times time. We have the Vx component, which we figured out earlier is 25.16. We need to find how long it takes. To do that, we can use the variables we have from our previous point, and we can say, and we know from kinematics equations that our final velocity equals our initial velocity plus acceleration times time. Do some basic algebra, and we'll get our velocity minus our initial velocity divided by acceleration equals time. These are all y components of velocity. Plug those numbers into a calculator, and it will take the rock 4.08 seconds to hit the ground from the moment it's thrown. So we can take that, throw that into our RVT equation. So time 4.08 seconds times our x component velocity of 25.16 meters per second will give us a total range of 102.65 meters. For the final part of the problem, we need to draw the graphs of our x of t, y of t, vx of t, and vy of t. So our x of t, since we're traveling at a constant velocity, we know the slope will be positive. Start from our origin point, going horizontally at a constant rate. This gives us a straight line. To get our vx of t, we can take the derivative of this, which will give us a constant slope, zero slope, because our vx is constant and does not change. Our y component is going to look really just like our trajectory path if viewed from the side, to where it'll start at we'll start with a positive amount. It'll go up to a point it hits peak, come down for a little bit. This isn't drawn perfectly to scale. we will cross our 0, which I put it at the top of the building, and head down to the rocket's negative 15 meters at our 4.08 seconds. Taking the derivative of that, you can get the velocity, the y component of the velocity graph, which will just be, since this is concave down, we'll get a negative constant slope, and it will just go like that from 16.3 to negative 23.7 over our 4-second interval.